Measurements. Physics is a basic discipline in the category of natural sciences. Man has always been curious about the solar system, the sky at night, the moon, annual cycle of seasons, volcanoes, etc. The human life and various phenomena related to it have been a sources of inspiration to do new searches for knowledge. While studying physics, at one end we have to deal with phenomena at a very small scale of length, like size of nucleus, size of atom. At the other extreme, we are facing phenomena involving motion of planets, size of galaxy, etc. Hence, we need to standardize the methods for measurements which are consistent everywhere. Need for measurements. If you are going to decorate your house, you will have to measure the things you want to get to make sure if they will fit inside. If you are going on a trip, you will want to know how many miles you will be traveling. So without doing measurement, the simple things we do every day would be difficult. Experiments and measurements form the basis of physics. Experiments help us to measure and study various phenomena in physics. By a comparison of the results of the accurate measurements with the numerical predictions of the theory, we can gain considerable confidence that the theory is correct, and we can determine in what respect it needs to be modified. Physicists think about the measurements and need to have a much more sophisticated understanding of the measurement process than normal people do. Units of measurements. The reference standard used for the measurement of a physical quantity is called a unit. It is a definite magnitude of a physical quantity defined and adopted by convention and/or by law that is used as a standard for measurement of the same physical quantity. Any other value of the physical quantity can be expressed as a simple multiple of the unit of measurement. A good unit should have the following properties. It should be easily available. It should be invariable, that is, it should not change with space and time. It should be reproducible. It should be universally accepted. As stated earlier, knowledge of measurement can be used for studying interesting phenomena like measurement of distance of different stars from the Earth or measuring distance between the Earth and the Sun, etc. In order to calculate how far away a star is, astronomers use method of parallax. As the Earth is revolving around the Sun, near stars seem to shift their position against the further stars. This is called parallax shift. By knowing the diameter of the Earth's orbit and observing the distance of the shift, astronomers calculate the parallax angle across the sky. The smaller the parallax shift, the further away from Earth the star is. System of units. A set of fundamental and derived units is called a system of units. Following are some examples of system of units used in which the base units of length, mass and time were as follows. CGS system, centimeter gram second system. MKS system, meter kilogram second system. FPS system, foot pound second system. SI units. The International System of Units, abbreviated as SI, is the modern form of the metric system and is generally a system of units of measurement devised around 7 base units. The SI system has now replaced all other system of units and has greatly simplified exchange of scientific data between different parts of the world. The SI was developed in 1960 from the old meter kilogram second system rather than the centimeter gram second system, which in turn had a few variants. Because the SI is not static, units are created and definitions are modified through international agreement among many nations as the technology of the measurement progresses and as the precision of measurement improves. Fundamental and derived quantities. Fundamental quantities. The physical quantities, which do not depend upon any other physical quantities for their measurements, are called fundamental quantities. For example, length, mass, time. Derived quantities. Physical quantities other than fundamental quantities, which depend on one or more fundamental quantities for their measurements, are known as derived quantities. For example, speed, density, force. Fundamental units are the units used for measurement of fundamental quantities, and derived units are used for measurement of derived quantities. The 7 basic physical quantities, along with their symbol and SI unit, are given below. Among these 7 fundamental units, candela is fundamental unit of luminous intensity, which is defined as luminous intensity observed from a source of monochromatic light having very high frequency that has an intensity of 1 upon 683 watt per steradian. Units radian and steradian may be used advantageously in expressions for derived units to distinguish between quantities of a different nature but of the same dimension. Some conventions to be followed while writing SI units are given below. Full name of unit always starts with a small letter even if named after a person. For example, Newton, Joule. Symbol for unit named after a person should be in capital letters. Symbols for all other units are written in small letters. Symbols of units are not to be expressed in the plural form. Full stop and any other punctuation mark should not be written after the symbols. Measurement of length by parallax method. plus x2 plus x3 up to xn upon n. Absolute error. The magnitude of the difference between mean value and each individual value is called absolute error. Absolute error for x1 is equal to delta x1 is equal to xm minus x1. Similarly, in the measurement x2, it is delta x2 is equal to xm minus x2 and so on. Mean absolute error. It is nothing but an arithmetic mean of all the absolute errors. Mean absolute error for x1, x2, x3 up to xm is shown below. Relative error. The ratio of the mean absolute error to its most probable value is called relative error. Relative error is equal to delta xm upon xm. Percentage error. Percentage error is the relative error into 100. Percentage error is equal to delta xm upon xm into 100%. Note: if delta x is error in x and delta y is error in y, then percentage error in xy is delta x upon x plus delta y upon y into 100. If delta x is error in x and delta y is error in y, then percentage error in x upon y is delta x upon x plus delta y upon y into 100. If delta x is error in x, then percentage error in xn is n into bracket delta x upon x bracket complete into 100.